All right, welcome and thanks for joining for the optional video. It's always fun to have you here. Solve for x, we've got sine of 2x plus cosine x equaling 0. So this is a case where, like, looking at this, I cannot solve it because it's written right now as two different trig functions. So what I'm going to want to do is use the double angle formula for sine to say that this is the same as 2 sine x cosine x plus cosine x equaling 0. And now what that's going to allow me to do is see here that cosine could be factored out. And I'm left with 2 sine x plus 1. So each of these at this point can now be solved separately. I'd have cosine x equaling 0, which is great. It's already solved. And sine x equaling negative 1/2. I did the solving there real quick. So each of these we go and we draw our little unit circle. Looking here, cosine x being 0 would be here and here. So this is going to be x equals pi halves, the smaller angle. And these are, again, equidistant with a distance of pi. So that's giving me the period of this, n pi. Over here, sine being negative 1/2 happens here and here. These points are not equidistant. You know, if we're talking about here versus here, we've got something that's less than pi and something that's more than pi. So each of these need their own equation. This angle is 7 pi sixths. Plus, what I'd have to do to get back to this point would be add 2n pi. And here, this angle is 11 pi sixths. And same thing, I'd need to add 2n pi. So you've got three solutions for that equation. All of them would be required. Next, we've got the sine of 2x times the sine of x is equal to the cosine of x. So the first thing, I'm going to move this cosine over. I get sine of 2x sine x minus cosine x equaling 0. Now, you might be thinking like, well, what about when I multiply these? You cannot multiply them because they have different arguments. So it's sort of like the idea of like them not being like terms because they have different things inside the sine function. But you can rewrite the sine of 2x as 2 sine x cosine x. Now that is just me rewriting the sine of 2x. So I still have another sine x from here minus cosine x equaling 0. And then to clean this part up, now I can multiply the two sines because they have the same argument. And when I multiply those, I get sine squared x. Cosine x minus cosine x equaling 0. Looking at this, I see that there are two terms and cosine can be factored out of both. So I'm left with 2 sine squared x minus 1 equaling 0. At that point, I can now solve just by setting each one of these equal to 0 separately. So I get cosine x equaling 0. I get sine squared x equaling 1/2, which means the sine of x is equal to plus or minus root 2 over 2. And I go and I reference my unit circle. So here, cosine being 0, you know, it's been in like every problem so far. That's just going to be pi halves plus n pi. Over here, sine being plus or minus root 2 over 2 happens in 4 locations. And this is a cool problem because if you think about the distance between these, and you've seen problems like this, but you may not have asked about it, the distance between all of these is pi halves. So this is a rare case where you're not looking at just 2 of those points being equidistant. You're looking at all 4 of those being equidistant. And what that tells us is we can write it as one equation, starting with the smallest angle, pi fourths, plus whatever the period is. So here, the period is only going to be pi halves, and we put that little n in front of it. So x equals pi fourths plus n pi halves. And again, that's just saying that this repeats, or you can get to a solution every pi halves. All right, next we've got the tangent of 2x minus the cotangent of x. So we sort of got a lot to go on in this problem. You know, tangent problems are always a little bit longer. If I rewrite this tangent of 2x, what I get there is 2 times the tangent of x over 1 minus tangent squared x. And if you think about what cotangent is just 1 over tangent. So, you know, what we're looking at now is probably trying to get some common denominator so that we could try and simplify this a little bit. On the left, I'm going to multiply by tangent x. On the right, I'm going to multiply by 1 minus tangent squared x. And again, I'm doing this on top and bottom. So I get 2 tangent squared x minus 1 plus tangent squared x over tangent x times 1 minus tangent squared x equaling 0. And sometimes I don't multiply out that denominator. I try and wait and leave it. I just sort of want to see what's going to happen with that. So combining my numerator, 2 tangent squared x plus tangent squared x is going to give me 3 tangent squared x minus 1 over tangent x 1 minus tangent squared x is equal to 0. Now, looking at this denominator, in that denominator, we're talking about trying to solve for something being equal to 0. The denominator would never help me get this to be equal to 0. The denominator would come into play with things like domain restrictions. You know, technically, tangent x cannot be equal to 0, and 1 minus tangent squared x cannot be equal to 0. Because if either of those two things are equal to 0, this would be over 0, which means it would be undefined. So while it isn't going to be super important, something to keep in mind is here, tangent can't be equal to 0, so those are those locations. X cannot be equal to n pi. And here you would get tangent being plus or minus 1. So x cannot be equal to pi fourths plus n pi halves. Cannot be equal to. So these are just domain restrictions because they would give the denominator equal to 0. But as long as we have those in mind, now what we're able to do is just sort of wipe off this denominator. You know, you're multiplying by the denominator on both sides because that can never get me to be equal to 0. So we're left with just 3 tangent squared x minus 1 equals 0. So we get tangent squared x is equal to 1/3. So tangent is equal to plus or minus the square root of 1/3, which gives me tangent is equal to plus or minus root 3 over 3. And if we go and draw that on the unit circle, that's all of these locations. 2 of them are equidistant from each other. You know, these 2 points would be equidistant. So I could write that as one equation, pi sixths plus that distance is n pi. My second one, 5 pi sixths plus also n pi. So those domain restrictions didn't really come into play here. If for some reason I had gotten something that was like right here as a solution, I'd have to reject it because of this. All right, and then we have like sort of a long problem. Rewrite sine to the 4th x as a sum of powers of the cosines of multiple angles. So even those instructions, rewrite sine to the 4th x as a sum of first powers of cosines of multiple angles. So, you know, it's pretty packed. So first, I could rewrite sine to the 4th as sine squared x times sine squared x. And what I can do then is apply the power reducing formula. If you're looking at your packet, you're looking at the slide right above it. Sine squared u is equal to 1 minus cosine 2u. So this is going to be 1 minus cosine 2x over 2 times 1 minus cosine 2x over 2. And what I'm going to do now is just multiply these two things together. In the denominator, I'm going to get 4. In the numerator, I'm going to FOIL this. So 1 times 1. The negative cosine 2x and negative cosine 2x will give me negative 2 cosine 2x. And negative cosine 2x times negative cosine 2x is going to give me a positive cosine squared of 2x. And at this point, you have sort of a weird thing that happens because we just did the power reducing formula to rewrite sine squared and sine squared, but now we're left with another squared. So we're going to have to do another power reducing formula on this. Let's just switch colors real quick. On this, we're now going to do the cosine power reducing formula. And that power reducing formula says that the cosine squared of u is equal to 1 plus cosine of 2u over 2. So with that in mind, the cosine squared of 2x, notice that u is being replaced by 2x, or 2x is being replaced by u, will be equal to 1 plus the cosine of 2 times whatever the angle was. The angle in this case was 2x over 2. So this becomes the cosine squared of 2x being equal to 1 plus the cosine of 4x over 2. Okay, so keeping that in mind, coming back here, I'm going to factor this 1/4 out of all of this. So this becomes 1 minus 2 cosine 2x plus, and now I just went through how I could rewrite cosine squared of 2x as 1 plus cosine of 4x over 2. It might seem weird, but now I'm going to redistribute that 1/4. The only reason I factored it out is because if I substitute it in right away, you'd have this fraction that's part of a trinomial, that's part of a fraction, and I felt like that was going to be even more confusing than this entire problem in the first place. So if I redistribute this 1/4, I get 1/4 minus cosine of 2x over 2, because of the 2 over 4, plus 1 plus cosine 4x over 8. So now this is 1/4 minus cosine 2x over 2 plus 1/8 plus cosine 4x over 8. And the 1/8 and 1/4 can be added together. So my final answer here would be 3/8 minus cosine 2x over 2 plus the cosine of 4x over 8. And now I know that that's a final answer because it meets all of the ridiculous requirements, that the question asked for. It is the sum of first powers, so all of this is cosine to the first, of cosines, cosines, only cosines, of multiple angles. So I have a double angle and I have like a 4 times angle, which is fine because it said I could have multiple angles. Now, don't look at that and be like, whoa, I can never do that on my own. It's not like a super common question, but it is a super cool question, and it is something that you should be able to follow. All right, one last example. Given the triangle to the right, find the cosine of theta over 2. So looking at our triangle to the right, we know that this is a 3, 4, 5. We're going to ignore the fact that right now, the way that it's drawn, it's really like a second quadrant triangle. Because they said it's positive 3, positive 4. This is technically in the first quadrant. So we have cosine of theta over 2 is equal to plus or minus the square root of 1 plus cosine u over 2. The cosine of u just means, in this case, the cosine of theta. And the cosine of theta in this case is 4/5. So this is going to become plus or minus the square root of 1 plus 4/5 over 2, which becomes plus or minus the square root of, if I add that, I get 9/5 over 2. 9/5 over 2 is going to give me plus or minus the square root of 9/10. And this will give me plus or minus the square root of 3 root 10 over 10. So I did the square root of 9, and I rationalized to the square root of 10. So, I skipped one step that I'm hoping that you can be able to follow. If not, just write out that extra step. Square root 9 is 3 over square root 10, and then rationalize. And then last, doing this same type of question, or a similar question, not a half angle, with an expression. If I have the sine of 2 arc cosine x, remember that arc cosine x. The answer to that is really just some angle, theta. So this is asking for the sine of 2 theta, which is the same as 2 sine theta cosine theta. What this arc cosine x helps me do, though, is set up a triangle to represent the scenario. So if this is theta, cosine is x over 1. So this third side is 1 minus x squared, square rooted. And now all I have to do is substitute into the formula. So 2 times the sine of theta, square root 1 minus x squared, times the cosine of theta, x. So this becomes 2x square root 1 minus x squared. All right, that's it. Those are some weird examples. This one a little bit weird, always just the understanding of what this is actually telling us. This one, super sort of long, complex problem, but super fun, very interesting. I know you had fun going over it. And then the types of questions from section 5.3, which really are like the heart of 5.5, knowing how to do things like these ones and have that down and be able to work through them pretty quickly. Jot down if you have any questions so that you can ask those. And otherwise, just get started on some of that 5.5 bookwork.